Ever notice your phone charger getting warm or your laptop heating up? That's wasted energy, all thanks to electrical resistance. Imagine electricity as a flow of electrons moving through a wire, like people rushing through a crowded hallway. The electrons bump into each other in the walls, creating friction. In electricity, this friction is resistance. Resistance slows electrons down, so we need more energy to keep them moving. The lost energy turns into heat, why your devices get warm. This happens everywhere, from power lines to tiny circuits in your smartwatch. It's like carrying water in a leaky bucket. By the time it reaches your home, some is lost. Copper has low resistance, making it great for wiring. Rubber has high resistance, making it a good insulator. But what if we could find a material with no resistance at all, where electrons flow freely, with zero energy loss? That would be a game changer. It would be super. Imagine electricity flowing forever, without losing any energy. That's superconductivity, a real phenomenon where certain materials conduct electricity with zero resistance. It's like our crowded hallway suddenly becoming an empty, endless freeway for electrons. But this state only happens under specific conditions, mainly temperature. Every superconductor has a critical temperature, or TC. Above it, resistance is normal. Below it, resistance vanishes. In 1911, Heike Kamerlingh-Onnes discovered this with mercury at just 4.2 Kelvin. Resistance dropped to zero. For decades, superconductivity was only possible at near absolute zero temperatures, making it impractical. The breakthrough came in the 1980s with ceramic materials that superconduct at higher temperatures, cooled with liquid nitrogen instead of expensive helium. This opened new possibilities, but the dream is a superconductor that works at room temperature. That would revolutionize everything from power grids to transportation. The quest for higher temperature superconductors is one of the most exciting frontiers in physics. We're getting closer, but the ultimate goal is still ahead. Superconductivity isn't science fiction. It's the future, and it all starts with zero resistance. How does a material suddenly lose all resistance? The answer: Cooper pairs. In a superconductor, electrons team up in pairs, like a buddy system thanks to the BCS theory. Normally, electrons repel each other, but cooled below the critical temperature, the crystal lattice helps them pair up. One electron moving through the lattice attracts positive nuclei, creating a tiny region of positive charge. A second electron is drawn into this region, and together they form a Cooper pair. These pairs move as one, gliding through the lattice without losing energy. It's like two friends on a skateboard rolling smoothly over a bumpy mattress. Together, they don't get slowed down. The quantum rules protect these pairs from scattering so they flow without resistance. All the Cooper pairs move in unison, creating a supercurrent. This collective dance is what makes superconductivity possible. It's a quantum phenomenon. Strange, but real. And it's the secret to zero resistance. Superconductivity isn't just about zero resistance, it also expels magnetic fields, thanks to the Meissner Effect. When a material becomes superconducting, it pushes out any magnetic field inside, becoming a perfect magnetic shield. Place a superconductor above a magnet and cool it below its critical temperature. Suddenly, it levitates. The superconductor creates an opposing magnetic field repelling the magnet below. This force is strong enough to counteract gravity, making the superconductor float. It's not a trick. It's a defining feature of superconductors. The Meissner Effect enables magnetic levitation, or MagLev. The floating object is suspended by invisible magnetic forces with no friction. This perfect diamagnetism is a spectacular consequence of superconductivity's quantum state. Levitation isn't just cool, it's proof of a superconductor at work. Not all superconductors are the same. They fall into two main types: Type 1 and Type 2. Type Y superconductors, like pure metals, expel magnetic fields completely but only up to a certain strength. Go beyond that, and they lose superconductivity instantly. They're all or nothing. Type 2 solutes. Superconductors, usually alloys or ceramics, are more complex and practical. They have two critical magnetic fields. Below the first, they act like Type 1. Between the first and second, they enter a mixed state, allowing some magnetic field in, but still conducting with zero resistance. magnetic fields penetrate as tiny tubes called flux vortices, but the rest of the material stays superconducting. This makes type sensibilidad superconductors ideal for powerful magnets like those in MRI machines and particle accelerators. Type 1 is pure, but fragile. Type sensibility 2 is tough and versatile. That's why Type 2 superconductors are the backbone of real-world applications. The difference is all in how they handle magnetic fields, and that's what makes them super useful. Superconductivity gets even stranger with the Josephson effect. Put two superconductors together, separated by a thin insulator, a Josephson junction, and Cooper pairs can tunnel right through, creating a supercurrent with no voltage. Apply a voltage, and the current oscillates at a precise frequency, the AC Josephson effect. This quantum tunneling is the basis for SQUIDs, superconducting quantum interference devices. A SQUID is a superconducting loop with Josephson junctions, making it the world's most sensitive, magnetic field detector. It can sense changes billions of times weaker than Earth's magnetic field. SQUIDs are used in brain and heart research, and in fundamental physics, all thanks to the weird, wonderful world of quantum superconductivity. Superconductors are already transforming our world. MRI machines in hospitals use superconducting magnets for detailed body scans, impossible with ordinary magnets. MagLev trains float above tracks using superconducting magnets, reaching incredible speeds with no friction. Superconducting power cables can transmit electricity with zero loss, making grids more efficient. Pilot projects are already replacing copper cables in cities. Particle accelerators like the Large Hadron Collider use thousands of superconducting magnets to smash particles together and unlock the secrets of the universe. Superconductors are essential for scientific discovery and modern technology. From medicine to transportation, they're making the impossible possible, and this is just the beginning. We've gone from warm phone chargers to quantum levitation and maglev trains. Superconductivity is a gateway to a faster, more efficient future. The holy grail is a room-temperature superconductor. Perfect efficiency, no cooling needed. Imagine power grids with zero loss, ultra-efficient motors, and computers that never overheat. It would revolutionize energy, transportation, and technology. The discovery would be as transformative as electricity itself. The story of superconductivity is about human curiosity and pushing boundaries. With science, the future isn't just bright, it's super.